Hi everyone, welcome to CAIE Science, and today we will be solving October November 2022 variant 2.1, or you can say 2.3 because 2.1 and 2.3 variants are the same of 970. Okay, let's begin. Question number 1. Atoms with nuclei containing an odd number of protons tend to have fewer isotopes than those with an even number of protons. Okay, gallium has two stable isotopes, gallium 69 and gallium 671. Okay, table 3, table 1.1 show, complete the table 1.1 to show number of protons, neutrons and electrons in the two stable isotopes of gallium. Okay, so you have to tell number of protons, neutrons and electrons. Okay, so now let's see what is the proton number of gallium. Okay, so this is the gallium. You can see that it has proton number or atomic number of 31. Okay, 31. So 31 is the proton number, and proton number is the number which gives an element identity of an element. Okay? If this proton number changes, the element will be changed, okay, or the atom will change. So this will be 31 in both of these isotopes. Okay? And in isotopes, you know that there are only number of neutrons which are different. Okay, and how we are going to calculate number of neutrons? 69 minus 31 and 71, 31 minus 31. So you will get number of neutrons, because this mass number is also called nuclear number, and nuclear number is number of protons plus number of neutrons. So from subtracting this number of atomic nucleon number from this proton number, you will get number of neutrons. And now these are both atoms. Okay, so in atom, the overall charge, there is no overall charge, so it means number of protons and number of electrons are the same. Okay, so it will have this 31 electrons in both. Okay, define relative atomic mass. So relative atomic mass is the average mass of an isotopes of an atom compared to the 1/12th mass of carbon 12 atom, or you can say a unified atomic mass. Okay, so it's the ma average mass of isotopes of an atom compared to unified atomic mass, to the unified atomic mass unit. Okay, and unified atomic mass unit has a definition. It is the 1/12th mass of carbon 12 atom. Okay, so you can also write that as well. Part 3. The relative atomic mass of gallium Ar is 69.723. The relative isotopic masses of gallium 69 and gallium 71 are these. Okay. Use this information to calculate the percentage abundance of gallium 69 in the elemental gallium. So you are working. Okay. Assume that the element contains only these two isotopes. Give your answer to 4 significant figures. Okay, now you are given the uh, isotopic masses and a relative atomic mass, so you have to calculate the abundance of this isotope gallium 69. Okay, so I'm um, writing the abundance of this isotope as x. Okay, so 68.926 into x divided by 100, okay, plus 70.925 into 100 minus x, because if this gallium 69 has the abundance of x, then the abundance of 71 will be 100 minus x, okay, is equals to 69.723. This is your AR. Okay, that's how you calculate the abundance or relative atomic mass. Okay, this is the way. Okay, so from here you will calculate the value of x. Okay, so you can calculate the value of x, and the value of x is going to be um, like 60.13. You can calculate by yourself. Okay, I hope you can calculate it. Okay, so I'm just writing this answer. Okay, let's move to the other question. Part B. Okay, part B. Potassium also has two isotopes. Okay, both isotopes have same chemical properties. Then why the both isotopes of potassium have same chemical properties? So the chemical properties of an atom or element depends on the electrons. Okay, and in both isotopes the number of electrons will be same, because in isotopes only number of neutrons are different. So the arrangement of electrons in the shells will also be same. So they have same electronic configuration. Electronic configuration. Okay. State the full electronic configuration of an atom of potassium. Okay. So potassium, you see from periodic table, this is your potassium, and it has 19 proton number. Okay. This is the potassium has proton number of 19. Okay, so it will have 19 electrons. Okay, now write the full electronic configuration. So 1s2, then 2s2, 2p6, 3s2, then 3p6, sorry, 3p6, 3p6, then you have a 4s1. Okay, so this is the full electronic configuration of potassium atom. Okay, part 3. The first, second and third ionization energies of potassium are these respectively. Use this information to explain why potassium is in group 1. Okay, why it is in group 1? Because you can see that there is a huge jump between first ionization energy and second ionization. You can see that, and there is an not uh, that great jump between second and third ionization energy. So this big jump in between the first ionization energy and second ionization energy shows that it only has one electron in its outer shell, and this second electron is removed from inner shell. Okay, so inner shell will have a lower distance from the nucleus, so it will have a greater attraction to the nucleus. Okay, so what will you write? uh, there is big difference or big increase or big jump in first and second ionization energy. Okay, so it means the second and third electrons are removed from inner shell. Okay, so it means second and third electrons electrons are removed from inner shell. Okay, that's why this potassium is in group 1. Okay, so it has only one electron at its outer shell. Okay, moving towards question number 2. Magnesium shows reactions typical of group 2 metals. Okay, draw a label diagram to show the bonding in magnesium metal. Okay, so in metals there is a metallic bonding, and that's how metallic bonding is shown. There are positively charged ions in the sea of electrons. Okay, so that's how this looks, metallic bonding. So you, and these are the your free electrons. Okay, these are your free electrons. This minus charge is your free electrons. So this is uh, positively charged ions, positive ions, and these are your free electrons, free or delocalized electrons. Okay, moving towards question number part B. Part B. Figure 2.1 shows some reactions of magnesium and its compounds. Okay, identify the other products of the reaction 1 and 2. Okay, so in reaction 1, magnesium reacts with acid HCl to form magnesium chloride, and it will also form hydrogen gas. Okay, and for reaction 2, which this is reaction 2, so in reaction 2, magnesium carbonate reacts with HCl, so it will form magnesium chloride plus carbon dioxide plus water. Okay, so what are the other products? You have given magnesium chloride, and in reaction 1 the other product is going to be hydrogen. Okay, H2 or hydrogen. And in the uh, second equation, reaction 2, you have carbon dioxide and water is the other products. Okay, in reaction 3 is used to form precipitate magnesium hydroxide from magnesium chloride. Okay, state why calcium hydroxide would not be would not form precipitate of barium hydroxide from barium chloride. Okay, so reaction 3. In reaction 3, you are reacting magnesium chloride with calcium hydroxide. So this forms calcium chloride plus magnesium hydroxide. Okay, so now it's saying why why calcium and this magnesium hydroxide, by the way, forms a precipitate, because down the group the solubility of hydroxides, group 2 hydroxides, increase. Okay, and this magnesium is uh, will form a precipitate. Okay, and now it's asking you that why calcium hydroxide would not form a precipitate of barium hydroxide from barium chloride. So if you see in the periodic table, this is the magnesium, this forms precipitate, okay, with of magnesium hydroxide, but this barium is down the group. Okay, and down the group the solubility increases. Okay, so that's why the barium hydroxide will not form a precipitate. Okay, that's okay. So barium hydroxide is soluble. Okay, or you can write as the solubility of group 2 sulfates, solubility of group 2 hydroxides increase down the group. Okay, state the type of reaction that occurs in reaction 4. What is happening in reaction 4? the magnesium carbonate is changing into magnesium oxide. So if you see, if you heat the magnesium carbonate, it will form magnesium oxide plus carbon dioxide. So what type of reaction is this? This is the thermal decomposition reaction. Okay, so what type of reaction? Thermal decomposition. Moving towards next part, part C. 1 cm cube of magnesium chloride is placed in a test tube. Okay, a few drops of uh, silver nitrate are added, followed by a 1 cm cube of dilute ammonia. Okay, state in full what is observed in this experiment. So in this experiment, firstly, the white precipitate will form when you add the few drops of silver nitrate, because uh, magnesium chloride will react with silver nitrate to form AgCl, which will give a white PPT. Okay, and this AgCl will be soluble in aqueous this dilute ammonia. Okay, so this PPT will dissolve. Okay, so what will be the observation? Uh, Firstly, you will note the white PPT, then white PPT will dissolve. Okay, a white PPT or white precipitate, white PPT forms a white PPT form when silver nitrate is added. Okay, then PPT dissolves on addition of dilute ammonia or ammonia. Okay, so this is the observation. Okay, and this observation shows that this uh, compound contains a chloride ions. Okay, chlorides give a white PPT with silver nitrate of this AgCl gives a white PPT. Okay, part D. 1 cm cube of magnesium chloride is added to 1 cm cube of bromine. Okay, in a test tube. The solution remains orange. Explain why. Because the chlorine is more electronegative, and down the group reactivity of the halogens decrease. Okay, and this Br is not enough oxidizing agent to oxidize chloride ions. Okay, so what will be the answer? Bromine is not strong enough or too weak, not enough as a oxidizing agent to oxidize chloride ions. Okay, or Cl ions, Cl minus ions. Okay, because down the group the reactivity decrease, because the distance between the nucleus and valence electrons increase, so the nucleus will uh, less attract the incoming electrons. Okay, that's why chlorine is more reactive and bromine will not displace this chloride ions. Okay, question number 3. Some of the common chlorides of period 3 elements are shown in the list. Okay, from this list identify all the chlorides that have a giant late ionic structures in this solid states. Now you know that NaCl and magnesium chloride are both giant lattice. Okay, now let's talk about this LCl3. Okay, is this a giant ionic structure or it is an ionic covalent structure? So this LCl3 has both characteristics. It has ionic characteristics as well, and as well as covalent characteristics. but the covalent characteristics are in more more favorable. Okay, so that's why we don't consider this uh, as a ionic giant ionic structure. Okay, and if this Al2Cl3 Cl6, this is purely covalent. Okay, but this has some ionic characteristics, but we will consider this as a covalent structure. Okay, and because LCl3 can also react with water, this is also a proof that this has a covalent structure, because ionic solids dissolve in water, they don't react with water, but this LCl3 will react with water. Okay, so all the chlorides that react vigorously with water to form strongly acidic solutions. Okay, so LCl3 will react, LCl3 will react, SiCl4 will react, and PCl5. They are all will react. Okay, now the chloride that dissolves in water to form a neutral solution. So neutral solution has a pH of 7, and this is given by NaCl. And the magnesium chloride does not give a pH of 7, it gives a 6.5. Okay, quite little less than the neutral pH. Okay, so NaCl gives a pH of 7 in when dissolved in water. So NaCl is a correct answer, so you have to remember that. Okay, part 4, the chloride formed from the element with the highest melting point. Okay, so the chloride, you have to uh, identify the chloride formed from the element with the highest melting point. So if you know that this silicon has a giant structure and it has a higher melting point than the others in its period. Okay, you know the trend of melting points. Okay, now this is sodium, then magnesium, then you have aluminum. There is a small difference in the melting points between magnesium and aluminum. Then you have silicon. Okay, silicon has a giant structure, so it has a very high melting point. So the element is silicon, and the chloride of this silicon is SiCl4. Okay, part B. NaCl is one of the products of the reaction of chlorine gas and cold aqueous sodium hydroxide. Identify other products. Okay, so I'm firstly, let's write the equation. So when chlorine reacts with cold sodium hydroxide, it forms NaCl plus NaClO plus water. So you are given NaCl. The other products are NaClO and water. This NaClO is sodium hypochlorite. Okay, NaClO and water. Okay, PCl5 reacts with alcohols to form chloroalkanes. Okay, identify this type of reaction. Okay, this is a substitution reaction, because the alcohols have OH group, and this OH group is replaced with an halogen, or you can say a chlorine. So this is a displace substitution reaction. Okay, substitution. Draw the structure of the organic product formed in the reaction of an excess of PCl5 with butane 3 diol. So firstly, let's draw butane 3 diol. This is butane. Let's draw this as OH here, and 1 2 3 OH here. So this is butane 1,3 diol. Okay, and when it reacts with excess of PCl5, the both OH groups will be replaced by Cl group. Okay, so what will be the product, organic product? It will be um, 1,3 dichlorobutane. Okay, so this is going to be this organic product. Okay, let's move towards next question, next part. Sorry, part D. Sulfur reacts with chlorine to form several different chlorides. The most common are S2Cl2 and SCl2. Okay, SCl2 forms when sulfur reacts with an excess of chlorine. SCl2 is a cherry red liquid that reacts vigorously with water to form an acidic solution. Okay, use this information to deduce the bonding and structure shown by SCl2. Explain your answer. So it is a liquid, is a cherry red liquid. It is a liquid at room temperature. So this shows that it has a low melting point, and simple structures have a low melting points. You know that, right? Simple structures, they have a low melting point. Giant structures have um, very high melting point. So now you know that the structure is simple. Now the bonding. So it reacts with water. Ionic solids don't react with water, they dissolve in water. So if it reacts vigorously with water, that shows that it has covalent bonding, because it is hydrolyzed by water. Okay. So what is the bonding structure and bonding? It has a simple simple structure because low melting point, and uh, covalent bonding covalent bonding because it is hydrolyzed. Okay, moving towards next part. Calculate the enthalpy change of formation of SCl2. You may find it useful to use Hess's law to construct an energy cycle. Okay, so now you have to find the uh, enthalpy change of formation of SCl2. Okay. So now let's first write the uh, let's see the you can see the enthalpy change of formation has a definition. It is the enthalpy change when 1 mole of a compound is formed from its elements in standard state. So if you see here, these are the elements. Okay, and this Cl2 is formed. So this could be the enthalpy change of formation if only 1 mole of this Cl uh, S2Cl2 is formed. Okay, now let's write first the equation of reaction 2. S2Cl2 plus chlorine. Okay, chlorine gas. When chlorine gas, this is in liquid state. When they react, the reaction is reversible. So SCl2 is formed. Okay, this is also liquid. And what is the enthalpy change of this reaction? This is minus 40.6. Okay, so now if you want to calculate the enthalpy change of formation, so S8 is chlorine. Okay, so now the enthalpy change is the energy change for the formation of 1 mole of compound from its elements in standard states. So uh, this is going to be the enthalpy change of formation of SCl2. Okay, and we have to find this. So in the equation you have as 2 moles of Cl. So But in enthalpy change of formation, you have 1 mole, so we will write this as 2x. Okay, this is what we have to find. And now the enthalpy change of formation of SCl2, you are given the enthalpy change of this reaction, but this is not the enthalpy change of formation because 4 moles of S2Cl2 are formed. Okay, so now if you divide this minus 58.2 divided by 4, so you will have 1 mole of S2Cl2. Now this is your enthalpy change of formation of S2Cl2. Okay, I hope you understand that. Okay, now you can calculate the enthalpy change of formation of SCl2. Okay. So let's write the equation. The arrows which are head to tail will be right on the one side, and the arrow which does not show this trend will be right on the other side of the equation. Okay. So minus 8.42 divided by 4 minus 40.6 is equals to 2 multiply 2x. Okay. X is the enthalpy change of formation of SCl2. Okay, so from there you can get x is equals to minus 27.6. Okay, and this is your final answer, minus 27.6. Okay, moving towards next part, state the effect of decrease in pressure on the position of equilibrium in reaction 2. Okay, so the pressure effects if gaseous moles are involved. So if you see, there is one gas mole on the left side and 0 gas moles on the right side. Okay, so there are fewer gas moles on the right side. So if you increase the pressure, the equilibrium will shift to the right side. Okay, now, and this is saying that the pressure is decreased. Okay, so if the pressure is decreased, the equilibrium will move to left side. Okay, because there are fewer number of moles of gas on the right side. Okay, so equilibrium moves to the left side, to the left, because less number of gas moles on the right side, on the right side. Okay, or you can also write there are more number of gas moles on the left side. Okay, figure 3.1 shows the two structures of structural isomers of S2Cl2. Okay, isomer 1 and isomer 2. Okay, define the structural isomers. What is a structural isomer? This is the molecules with molecules or isomers with same molecular formula but different structural formula. Okay, molecules or compounds, molecules with same molecular formula and but different structural formula. Okay, moving towards next question, next part, suggest a value of for the ClSS bond in isomer 1. Okay, so this is asking in the bond angle of this part. Okay, so if you see here, let's redraw this. So if you see, the sulfur is in group 6 of the periodic table, so it will have 6 electrons in its outer shell, and 2 of the electrons are bonding, so remaining 4 will be in the form of lone pairs, okay, like this. So how many total pairs of so you have 2 lone pairs and 2 bond pairs, okay. So in total you have total pairs are 4, okay. So if total pairs are 4, um, and there are 2 lone pairs, so you will have a bond angle of 104, okay. You know that when there are 4 pairs total in total, and all 4 are bond pairs, so you have 109.5, which is a tetrahedral structure. Then if you have 1 lone pair and 3 bond pairs, you have 107, okay. And then you have if 2 lone pairs and 2 bond pairs, so then you have 104.5. So this will be 104.5, or you can write 104 as well. So bond angle is going to be 104.5, okay. And what is the explanation? Because there are 2 lone pairs and 2 bond pairs, okay. So sulfur has 2 lone pairs and 2 bond pairs, but the repulsion from lone pairs is greater. Why it is greater? Because lone pairs are more they more repel each other, so the repulsion from the lone pairs will be greater, okay, than the bond pairs, okay. That's why the shape is band shape, okay. Draw a dot and cross diagram to show the bonding in isomer 2, okay. So this is your isomer 2. So uh, show outer shell electrons only, okay. So let's redraw this here. Now you have to draw a dot and cross diagram. So you have sulfur, then you have another sulfur atom, then you have chlorine, and the other chlorine, okay. This is sulfur, Cl. Yeah. Now this sulfur is double bonded to the both sulfurs are double bonded, so they will share 2 electrons here, okay. And this both chlorines form a single bond, okay. So single electrons are shared, okay. Now the sulfur has 6 electrons in its outer shell, and 2 and 4 electrons are bonded, so now the remaining 2 will be like this. I'm showing this sulfur with X, okay, and this with dot, this sulfur. So this sulfur bonds only 2 electrons are shared in the bonding, and the remaining 4 will be like this. Now you have chlorine. Chlorine has 7 electrons because it is in group 7, okay. So only one of the electrons is shared, so the all the other 6 will be like this in the form of lone pairs, okay. So this is your dot and cross diagram. Moving towards question number 4, okay. Question number 4, organic compounds can be distinguished using chemical tests, okay. Table 4.1 shows 4 pairs of compounds, okay. You are given 4 pairs of compounds. Now complete table 4.1 to identify a reagent that could distinguish between the compounds in each pair, okay. You have to distinguish compounds from each pair, okay. Give a positive test result of the chemical test and identify which compound shows this result, okay. use a different reagent for each reaction. So you have to remember this. You have to use a different reagent for each test. Now for the first pair, okay. So you have ester and alcohol. So how you will differ? How you will use any the reagent which will differ? So you have to choose a reagent which reacts with one of them. Okay. So if I let's say if I choose sodium, okay, so sodium will react with this alcohol to form O negative N plus. Okay, the hydrogen will be substituted. Okay, that will, and this hydrogen released will show bubbles, effervescence. Okay, so the positive test, A2 will give a positive test. Okay, so what will be the positive result of this chemical test? A2 will give effervescence. Effervescence. Okay. Now B. So you have a ketone and an ester. So how you differ an ester from ketone? So the test for this carbonyl group is 2,4 DNPH. Okay, right? 2,4 DNPH. Okay, dinitroflan hydrogen. So the ketone will give a yellow or orange PPT with the 2,4 DNPH. Okay, so B1 gives orange PPT. Okay, now you have this C1 and C2. There is a double bond, so the double bond will react with a bromine water and aqueous bromine. Okay, and the color C2 turns solution to colorless. Okay, the solution will be colorless in C2. Okay, but the C1 will not react because there is no double bond. Okay, now D1 and D2. So you have a carboxylic acid and alcohol in this D2, and there are only alcohols in D1. Okay, so if you react sodium carbonate or any other carbonate, so the carbonates react with this acids to form carbon dioxide and water. Okay, but the alcohols will not react with the sodium carbonate. They can react with sodium, but they can't react with sodium carbonates. Okay, so the carbon dioxide will be released with the DTO. So the DTO D2, sorry, D2 gives effervescence. Okay, so you can see that we have used different reagents for each of these observations. Okay, and the marking scheme has also shown you some other uh, reactions as well, because and like you can use KMnO4 here in the first uh, reaction. Okay, you can use KMnO4. The KMnO4 will oxidize this OH group. Okay, the KMnO4 can't oxidize this ester. So the KMnO4 has a color of purple, so purple color will decolorize with A2. Okay, and with this B B1 and B2, the ketone is attached to the methyl group. So you can also use alkaline. You can use also alkaline iodine. Okay. Now moving towards next part. Okay, part B. C1 has a C1 has a melting point of -94 and boiling point of +49. Explain these properties by referring to the type of van der Waals forces between molecules. So this is a non-polar molecule. Okay? The dipoles cancel, so there will be only instantaneous induced dipole forces. Okay, and weak intermolecular forces. It has weak weak intermolecular forces. Okay, and because it only has instantaneous 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 and induced dipole forces, or dipoles, sorry, instantaneous or induced dipoles, sorry. So this is your answer. Okay, part C, draw a structure of cis isomer of C2. So C2, this is C2, and 1 2 3 4 5 6. Okay, you have 6 carbons, so let's draw a structure C6, and the double bond is on the second carbon. Okay, right? So you have CH like this, then you have CH3, CH2, 1 2 3 4 5 and 6. Okay, 1 2 3 4 5 6. This is your structure. Now this is cis isomer. You have to draw a structure of cis. So this is your cis isomer, CH3, C double bond, and you have CH2, CH3, and HH. This is your cis structure, cis isomer of C2. Okay, and this hydrogen will be rotated upwards. Okay, moving towards part D. C2 forms a polymer when heated gently. This is C2. This forms a polymer, okay, because it has a double bond, so it will form addition polymerization. Identified as the type of polymer that forms, so addition polymerization, additional or addition polymerization. Okay, draw a repeat unit, one repeat unit of the polymer formed from C2. Okay, so the repeat unit is going to be like this: CH3, and CH2, CH3. So this is your repeat unit. Okay, moving towards question number 5. Lectons are cyclic esters. Okay, under suitable conditions, lecton form from molecules that have both alcohol and a carboxylic functional group. Equation 1 shows an example for the formation of lecton. Now this is your equation 1. Figure 5.1 shows the synthesis of lecton P from M. Okay, M. This is M. So now draw M reacts with hot concentrated acidified KMnO4 to form N C6H10O3 in reaction 1. Draw the structure of N. Okay, so if hot concentrated KMnO4 is used, so this double bond will break down. So if you let's and this double bond will break down from here, and you will have the structure like this. Let's the correct one. uh, give me just a second to draw the structure so I can explain you clearly. This is the structure. Okay, now this double bond will break down. Okay, um, this double bond will break from here. Okay, from here. Okay, and then you will have a ketone group here. The oxygen will attach here, and you because there are only the carbon, this carbon has ketone, both uh, uh, carbon or alkyl group attached on both sides. Okay, and this will form an uh, uh, an acid. Okay, carboxylic acid, because this has this carbon. Let's make it bigger, bigger. Let's draw first this here. Okay, so this is a double bond, and this double bond will break down. Okay, let's break the double bond. Okay, then you will have this OH group. OH group will be attached here, and this there will be an OH group and OH, O group, carbonyl group, and this OH group. Okay, so this will form an ester and sorry, an ketone and an carboxylic acid. Okay, I hope you understand this. So this will be your N. Okay, so it is saying draw the structure of N. So you can draw it. Okay, so now let's draw the structure. You can now draw it in straight form. Okay, so 1 2 3 4 5 and 6. Okay, you have 6 carbons. So this is your ester part, 1 2 3 4 5 and 6. So this is your structure. Okay, structure of N. You can also calculate this MR molecular formula, so you will get C6H10O3. Okay, you can check this. Now the N is reduced by NaBH4 to form a 5-hydrohexanoic acid in reaction 2. Okay, now this ketone is reduced to OH by NaBH4. Okay, construct an equation for the reaction 2 using the molecular formula. Okay, using the molecular formula. So molecular formula of N is C6H10O3. So it will react with a reducing agent. In equation, use H plus. Okay, this H to represent one atom of hydrogen from reducing agent. So this will react with a reducing agent. So this will form this 5-hydroxyhexanoic acid. So this the double bond will break, and one OH H group will attach here, and one H group will attach here. So you will have two more hydrogens. Okay, so C6H12O. So yes, this. So you don't. Okay. So C6H12O3. So this is your equation for the reduction of N. Okay. Now in reaction 2, reaction 2 is nucleophilic addition reaction. Why? Why this is nucleophilic addition reaction? Suggest why reaction 2 creates an mixture of two organic compounds. Okay, so it is asking why reaction 2 creates a mixture of two organic compounds. Now this is an important part. So let's make this. So if you see, when I can write this part, because when the N is reacting with NaBH4. This part, okay, this part is not reacting. Okay, this part is not reacting, only this ketone is reacting. Okay, you know that when NaBH4 is reacting with on. So I can, if I write this as R, okay, I'm for let's say I'm writing this as R. Okay, R carbonyl, and then you have CH3. Let's suppose, okay, I want to show you a thing to make you understand this question. This part suggests why reaction 2 creates a mixture of two organic compounds. Okay, so if I redraw this here, CH3. Okay, let's erase this now. Now if you see here, um, the reaction 2 is a nucleophilic addition reaction. It already told you. Okay, so this is your nucleophile. Okay, now uh, you tell me this, if what is the bond angle of this. This has a bond angle of 120. Okay, and this also has a bond angle of 120, and this also has a bond angle of 120, because this is a trigonal planar structure. Okay, you can see that. So trigonal planar is a planar structure, so it is a planar structure. So the nucleophile can attack this partially positive carbon from any side. This can attract it from this, from upwards or from downwards. Okay, so it will form, let's say firstly it attacks from upwards. Okay, so you will get R group and C, and then you have nucleophile attached over here, and this double bond will break down, and you will have a CH3. Okay, let's suppose. Now if the nucleophile attacks from downward, you will get a CH3, then nucleophile, then R group, this. So can you see that these are both mirror images of each other? You can see that, right? These both are mirror images of each other, so they are optical isomers of each other. So that's why, because the N is planar, so nucleophile can attack from either side, so it will form a mixture of two organic compounds. Okay, so this is what it is asking here. Suggest why the reaction 2 creates mixture of two organic compounds. Why? Because N is planar, or you can say a ketone in this is planar. This is a ketone. Ketone in N is planar, so uh, can be attacked, can be attacked from either side. I hope I could clarify. Draw lactone P, the product of the reaction 3. Lactone P. So this is a lactone P. So you have a 6 carbon. 1, 2, 3, 4, 5, 6. Okay. So let's first draw this. Let's draw this 5 hydroxyl in a ring shape. Okay. So this will be like this. Which then you will have PH2, 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 and CH, CH3, and double bond. Okay, so this oh sorry, you will have alcohol over OH. Okay, so this part, this water will eliminate, and this will form an ester. Okay, so 1 2 3 4 5. Okay, so the ester will be like this: 1 2 3 4 5. Okay, so and you will have like ester linkage. There will be a branch over here, okay, of CH3. You can see that here. Okay, so there is a branch of CH3 because this is a secondary alcohol. Okay, you know that. So this is the shape of electron P. Okay, moving towards next part, part B. A student monitors the progress of the reaction 2 using infrared spectroscopy. Reaction 2. This is reaction 2. Use the table 5.1 to suggest why it is difficult to distinguish between N and 5-hydrohexanoic acid using infrared spectroscopy. So this is your N and this is your 5-hydrohexanoic acid. So you can see that they have a similar groups attached. This is the carboxylic group attached over L, and this is a carboxylic group attached over. So they will give a same peak, and the uh, so why it is difficult, because they have a same group, so they will give a same peak. Okay, you can see from this table that the carboxylic group will have a pH of OH at 2500 to 3000 at the carbonyl peak. So and this carbonyl peak will be also be given by the ketone. Okay, so it will be a little difficult to uh, see, because they have a same number of same functional groups, so the absorptions will overlap. Okay, so why they are difficult to distinguish? Because they will give similar absorptions. Okay, absorptions, because both have both have same bonds in similar environments. Okay, in similar environments. Okay, they have same bonds in similar environments. You can see that from the table. Okay, moving towards next part. The unknown electron Q is analyzed using mass spectroscopy. Okay, the table 5.2 shows the information from the mass spectrum. Okay, so it told you that this is electron. So and electrons are, you know that they are cyclic carboxylic acids. Okay, like this, or let's say like this. This is a cyclic carboxylic acid. So electrons are cyclic. Sorry, they are cyclic esters. Sorry. They are cyclic esters. Um, now uh, you know that the electron Q is analyzed using mass spectroscopy, and table 5.2 shows the information from the mass spectrum. So the Q is electron, so it must be a cyclic ester. Okay, use this data to deduce the structure of Q. So now you have to find out the number of carbon atoms. You know that it is electron, so now you have to just uh, find the number of carbon atoms, so you can deduce the structure of Q. Okay, so the formula to find the number of carbon atoms from this data is N is equals to 100 divided by 1.1 into abundance of N plus abundance abundance of m plus 1 peak divided by abundance of m plus peak. Okay, abundance of m plus peak. This formula, you have to remember this formula. Okay, and n is number of carbon atoms, so n is equals to 100 divided by 1.1. 1.1 is actually the abundance of carbon 13. Okay, multiply by abundance of m plus 1 is 3.15 divided by 95.5. Okay, so from here you will get the value of n is equals to 3. So you know that there are 3 carbon atoms, 3 carbons, 3 carbon atoms. Okay, so now you know that it is a lepton and there are 3 carbons. So now you can reduce the structure. Okay, so the structure is going to be like this. You will have this group will be a permanent, you know that, pH. Okay, now you will attach another carbon here, CH2, and this will be the, so this is your structure, and you can also draw it in a skeletal form as well. Okay, so this is your structure. You can show your working here, the working I showed here, you can show in these lines. Okay, so this paper is finished. I hope you understood everything, and if you have any queries you can ask me in comments. Okay, thanks for watching, and if you haven't subscribed my YouTube channel, do subscribe for more videos. Thank you.